Hello. In this part, we'll be looking into threads. In previous lectures, most of our discussion has been around processes, right? So as we know, a process contain everything that is needed for execution. Mainly, it contains an address space, basically the memory, which contains all the code and data, and it has resources that it has access to. For instance, all the files that it has opened and all the accounting information, for instance, number of CPU cycles used, so on and so forth. It also has execution state that indicates the current state of the process, basically the state of the registers, the CPU registers, and stack pointer and program counter. And we also saw how like various ways in which processes communicate with each other. So, and in lab 2, actually, you implemented a nice way in which processes can communicate. Basically, what processes do is at process creation time, parents pass all the information that is needed for the child processes at fork or at exec. And then using that information, processes can communicate with each other. There are two primary ways in which processes can communicate. One is using shared memory, the other is using message passing. In case of shared memory, we know that parent usually creates a shared memory and then passes that handle to the child processes, and child process use the handle, maps the memory into its address space, and then they can communicate by reading and writing through the shared memory. Okay. Here, once the memory is mapped, there is no mediation from the operating system. However, in case of message passing systems, the communication actually requires uh, operating system intervention in the form of system call. But in general, inter-process communication is expensive, right? Even in case of shared memory, system call needs to be made to allocate shared memory, and then similarly, that shared memory has to be mapped to the children process. So it's not easy. So in general, IPC mechanism between processes is expensive. Although now we have many optimized operating system implementations that actually provide lightweight IPC mechanisms to reduce overhead. But the overhead is still there. Let's look at a real world example where we need multiple processes. Okay, let's look at a web server example. So how does web server handles single request? So when a request comes for a web page, so web server fetches the web page and sends the response to the client. However, web server may need to handle many concurrent requests. Imagine if more than two clients are requesting a web page, then web server needs to serve both the clients. So one obvious solution is to let the parent process fork number of processes, and each of these process can actually serve each of the requests. And then furthermore, the children processes can communicate with the parent, or they can communicate with each other by using the inter-process communication mechanisms that we have seen before, either through shared memory or through message passing system. So now you can see that in general, to have a job, or like to have a program that has multiple processes, which we call parallel programs. In order to execute parallel programs, what we need to do is first we need to create several processes, okay, independent processes that can run in parallel. And then we need to set up an IPC mechanism, either through shared memory or message passing, so that these processes can communicate with each other. And then finally, we let the operating system schedule these processes in parallel, either logically or physically. By this, I mean, when you have multi-processor machine, like when you have multiple processors, then the processes can actually physically run at the same time. Whereas in case of single CPU machine, the processes actually logically run at the same time by CPU scheduling, right? However, this situation is very inefficient if you think about it, because anytime you need to run, you need to create a new process, then everything gets duplicated, right? First, we need to create a process control block, and that's not free, because we need to create the structure and populate all the entries with the valid values. And then we also, like for interprocess communication, there is also computation overhead by the operating system, because now operating system has to do some work in the PCB of two processes that they want to communicate with each other. So it's not exactly efficient. So there is a lot of overhead involved in creation of process, or in general, in case of parallel programs. But if you think about it, this seems to be useless. Why? Because all the processes, in case of, like, if we take our web server example, all the processes in the web server are cooperating. That means they all share the same code and data. They always execute the same code, right? All the processes, they execute the same piece of code, and they also have same privileges. So it's not that we handle one request with more privilege compared to the other request, right? We handle all the requests at the same with same privileges. Furthermore, all the processes actually share the same resources. They have access to the same set of files and same set of sockets, so on and so forth. The only thing that these processes don't share is their execution state. That means the state of CPU specifically, right? The state of CPU, and some stack data. Like, for instance, each process will be serving requests that comes from different users. So the user data, which we call like stack data, so that is different, and the CPU state is different. That's it. Rest all these processes have the same resources, like have the same thing. They all have exactly, they are exactly same except for the execution state. So creating processes for each of the to serve each request, in case of web server example, seems to be inefficient. So key idea behind thread is to separate process from its execution state. So we know that process contains everything including the execution state. So the key idea is, can we separate execution state out of process? Basically, now the process control block doesn't contain execution state. Okay, execution state is a separate entity from the process control block. Okay, now process is just address space, privileges, and resources, whereas execution state is now separated from the process. Okay? And this execution state is also called thread of control or thread. And this is the fundamental principle or like idea behind threads. So threads are basically different execution states for the same process. Okay. So modern operating systems, they support processes and threads. So where process is basically a container for the set of resources. So a process contains like address space, resources, and all the accounting information except for the execution state. The execution state is now saved in another structure called thread, which actually defines an execution unit. So now processes don't get scheduled, it's the threads that get scheduled. Okay. And there can be several threads that belong to the same process. So basically, that means they all share the same parent process, right? They all share the same resources. The only thing that is different is the execution state. And threads are the unit of scheduling. Now we no more schedule processes, we always schedule threads. Okay. And from the representation wise, so if you see, when we have a single threaded program or like a regular program, when we have only one thread of execution, right? So there we can see that all the code, like there is process control block, and then there is thread of execution, which has the execution state, which is registers and stack, right? And then when in case of multi-threaded program, we see that the things that are different for each thread are just the execution state, which is registers and stack. The code, data, and files are same for all the threads that belong to the same process. So this provides very nice flexibility for the operating system so that it doesn't need to do this additional maintenance of creating process control block when there is no need. Okay, especially in the web server example. So web server example, now if we look at web server example, there instead of creating processes, we can create threads. And all the threads, the only thing that is different is the stack, which is the user request, and the code that belongs to the web server, and the files that the web server can access, and the data that the web server, and the program data, it's all shared between all the threads. This is amazing. So now the overhead is very less. We just need to copy the execution state. Okay. So we have seen like now the process control block changes. So we have seen in the lecture 2 that process control block contains the execution state, which is the state of CPU and the stack. So now we take these two things away and then we put them in a different structure called thread control block, which contains two entities. The first entity is the shared information. Basically, it's a pointer to the parent process, pointer to the process control block that has all the resources. And then the other entity is private state, that is the execution state. So this execution state will be different for different threads, whereas the shared information could be common for the threads that belong to the same process. Okay, this provides very nice abstraction, right? We don't need to now maintain process control block for different processes that belong to the same parent process, like in case of web server. So now we maintain only thread control block for each thread, and we only schedule threads. We no more look at the processes, we only look at threads now. So programming with thread is very flexible, and it's error prone. Why? Because now the data is shared among all the threads. So if we don't uh, if we are not careful in accessing data, then we can have concurrency issues. Okay. um, like in case of C and C++, we can use pthreads that we have seen in few of our lectures before, where I've shown few examples in the class. So there, automatic variables, basically the variables on the stack, they are private to each thread, whereas global variables on like dynamically allocated memory by using malloc are shared. They are shared between all the threads. And furthermore, these threads, similar to the processes, these threads need synchronization in order to access shared data. Okay, and a thread library that is available in almost all the POSIX operating system, POSIX compliant operating system, is pthread, which stands for POSIX threads, of course. And then this is a simple example how we can use threads. So here we can see that we are creating two threads by using pthread create. Okay, and we are saying to the first parameter is the function that the thread should start executing. Okay, sorry, the first parameter is the pointer to the thread, whereas the third parameter, the print message function, that is the function that the thread should start executing from. So here, the main process, when we start, it creates two threads, thread 1 and thread 2, and we pass parameters message 1 and message 2 to thread 1 and thread 2. And finally, pthread join will make the main process wait for the threads to end. So basically now in this case, once we call pthread create, then everything is a thread. There is a main thread and there are two threads, right? Two children thread created by the main thread. So now pthread join will cause the main thread wait for the completion of thread 1. Similarly, the second pthread join will wait for thread 2. And finally, main thread ends by printing thread 1 returns and thread 2 returns. So in the next class, we'll be looking into more deeply about threads and how the scheduling happens within threads. Thank you.